Cell.
To sell.
Yeah. Hey everyone, welcome back to Cells to Sell. My name is Heem, that's Nick, and today we have Yi Fan with us. How you doing?
Hey everyone, my name is Yi Fan. I'm a MD PhD student here at Case Western.
Awesome, Yi Fan. Well, it's great to have you on.
Mm-hmm.
It's exciting to have another MD PhD on. We just had an undergraduate on last week. We've had some master students recently, so it's nice to get another glimpse in another another part of case, another glimpse, another perspective
For sure.
on being in a master's program and a PhD program. So let's just start off kind of normal, like, where are you from? Where'd you go to high school, college, and how did you get into this?
Yeah, sure. So I was actually born in Taiwan, and towards the sort of tail end of elementary school, my entire family moved over to the United States. So we are currently situated in New York City. I've always had an inclination towards science and math ever since I was young, and partly probably because we are from an Asian family as well. But in high school, I actually went to a science-focused high school, and sort of all of my peers had this sort of similar interest in the scientific fields, engineering fields. Although I was sort of alone in that I had a more biological inclination, again, maybe from an Asian parent influence of us wanting us to be doctors. But eventually, from high school, I went to Cornell University, where I studied a mix of biology, chemistry, and a little bit of physics, sort of trying to figure out what sorts of sciences I wanted to devote my life towards.
Yeah.
And I settled for something the more medical sciences, but never fully giving up the opportunity for research and investigation. And that eventually then brought me here to the MD PhD program, where I felt like I could commit myself to doing scientific research that still has benefit for a lot of patients around the world.
Yeah.
That's awesome.
I just have a follow-up question. What made you choose MD, PhD in research? You were surrounded by, you went to a math and science school where they're probably trying to push out a lot of maybe more engineers than biological sciences. So what was the turning point where you're like, I really want to do this? The math is great, but I really want to stick with research in biology.
That's actually an interesting question, because it had always been the case that I much preferred things like physics and chemistry more so than biology. I actually hated biology when I first started high school, because a lot of the ways that biology is taught is you need to memorize a basic list of facts. And that's how you do well in sort of early biological classes. And so I never really quite appreciated what these different concepts meant, right? But I also think it's really true that a good teacher does have a way of inspiring you. And I myself happen to be a very easily inspired person that, once I took an upper level biology class, it felt like she changed my entire perspective on how I should view the science, right? She would ask, for example, there's this molecule that, we use RNA, for example. We've known it for a really long time as a sort of intermediary between the genome and the protein coding, the coding proteins. In which case, how did people figure that out, right? It's the how and the why. And she always had this really high level of energy whenever she asked these questions. And I've just felt like just a simple act of asking why and how really changed my perspective on trying to understand how we came to learn about these different concepts. And so that was sort of my first sort of turnaround, where I began to sort of see how my own interest in chemistry and physics could be applied towards something that has a lot of therapeutic benefit, like biology, that has application towards actual people, and not so much focus on the test tubes and the lasers.
Yeah.
So that's for listeners who don't really know what this specific kind of research is called. It's called translational research, right? So you're trying to focus on research that has real therapeutic benefit for humans, and that's why you're pursuing an MD PhD, right? Because you want to one day maybe use these therapeutics in your own practice every day?
Yeah, I think that's the ultimate goal for this training program. Eventually, they want us to be physician scientists who can sort of juggle the intricacies of both. You can be a doctor who is an expert at a particular field and you treat patients accordingly. But hopefully, with your scientific background, you can sort of begin to gain a perspective on the underlying disease processes associated with our patients and use scientific techniques in the lab to help address the problems associated with those diseases, and maybe just push forward something new to give these patients a fighting chance.
Wow, that's
Yeah.
great. That is like the first time I've ever heard an MD PhD described like that.
Yeah, it's
You
like
know, that's a very very cool take on your program. I think it's really interesting, especially you're devoting 8 years, 9 years of your life to this, maybe
For sure.
10.
Yeah.
But no, that's great. And like I want to circle back though to your teacher.
Yeah.
And I had a teacher like that too, and I hope that everybody listening and everybody who gets to go through school has a teacher who can inspire them like that. I remember it was my junior and senior biology and anatomy and physiology teacher, Miss Sketch was her name, and she was great. And I was like, she's like, what are you gonna do after college? I was like, I think I'm gonna go into like nursing. I think I want to do nursing. She's like, why don't you just try to be a doctor? And I was like, She's like, you're smart enough. She's like, what? You might as well try it. And then that didn't work out. So I guess I wasn't smart enough. She was wrong. But now I'm here, right? And like, but that put me on that path of, you know, I just wanted to go in nursing because honestly, it's kind of a secure job.
Right.
You know, it's 4 years of school. You get out, you got one. But then, you know, I fell in love with biology, and I fell in love with wanting to work with humans and all that kind of stuff. So that's great. That's great.
Yeah.
Now, I have a question for you.
Sure.
So, you know how some people can be very inspired in their life because of a particular thing that happened to them or their family member. So they're like devoted to a particular disease state.
Yeah.
Whether that's some sort of cancer, whether that's some sort of liver disease, anything. So the work you're doing right now, which I guess we can go into for your PhD, how have you geared your PhD toward that particular field, and how did you get interested in that field?
I think it all started with sort of my own interest in chemistry and physics. Like, again, in the beginning, that has always been my natural inclination. I've always been better at those fields than standard biological sciences. So I always felt like I wanted to at least retain some of that interest towards my own research. And sort of currently my field is chemical biology. So a central aspect of what I do is we take molecules and we make modifications in interesting ways so as to allow us to manipulate biological systems. And when we have the ability to do that, we can begin to make new discoveries about how biology is able to regulate itself in interesting ways. And along with that, maybe opportunities for new therapeutics. And I sort of see new therapeutics as an important aspect of what I do, again, from a medical science perspective, where we're giving people a second chance. We're giving them that new opportunity to try to put their lives in a better place than they were before. And I sort of see that as a central mission to this MD PhD program that I'm trying to do, where I want to design new ways through scientific investigation to help people.
Would there ever be a world where you just, you know, let's say your work now went really well, you know, there was a translational opportunity where you were able to, you know, take it from, you know, the lab you work in into market and maybe sell it to a big pharma company. Would you continue to work in research and were you like, okay, like that was exhilarating, like this is what I want to do for the rest of my life? Or would you still try to like balance the clinic and research as a medical scientist?
I think that's a challenging question. You know, it is true that oftentimes that as one begins to have their careers figured out, that they tend to gravitate more towards one or the other. Ideally, I like to be able to do both.
Okay.
To the best extent that I can. I think there is that inherent element of human interaction that I really enjoy about medicine, just talking to people, learning about their stories, learning about the challenges that plague them. I think that's something that is very much isolated from just typical academic research. And I ideally would like to be able to keep that in my career. It sort of reinforces the reason why I'm engaging the investigation in the first place. So I feel like that, as a very easily inspired person, that will have a major role in what I do in my future career.
That's awesome. That's awesome. I think that's why I picked this program, is because like I love the balance that the name gives, regenerative medicine and entrepreneurship. And you know, I love working with people. I worked in the service industry until I came to Case Western, and I just love talking to people, interacting with them, whether it was for 5 seconds or for 5 minutes, right? And I think that's one thing that kind of made me gravitate towards the medical field too was, I wanted to be a doctor because I wanted to talk to people. I wanted to hear their stories. I wanted to, try to have an understanding of what was going on in their lives and how I could maybe help them. So I don't know if you felt the same way. I know you were health sciences and all that kind of stuff.
Yeah, I was pretty much pre-med coming into the medical field, but I feel like living a life of purpose, because once you achieve money, everyone talks about it. Every wealthy person, they always say love is more important than money. So I think the medical field is a good balance between you do something very important for people, you feel fulfilled at the end of the day, and you earn a good amount of money. So it allows you to be more fulfilled as a person in the long term, and it's hard. It's really hard.
I want to talk about Cornell for a second.
Yeah.
What was it like? What was it like going to an Ivy League school, especially being in a STEM major? What was the atmosphere like? Was it competitive? Was it high stress, high tension all the time?
Worse than Cleveland.
Yeah, was the weather bad?
It's in Ithaca, right?
It's in Ithaca, New York. So addressing the weather question first, it's actually not as bad as what one could imagine. I think latitude-wise, we're actually pretty similar to where Ithaca is. So the climate is overall pretty similar. As a STEM major at Cornell, I've actually felt that high school was a much more competitive time for me.
Oh, wow.
There was a lot more pressure from my peers that I had to excel and perform well, whereas I didn't feel that nearly as much from Cornell. I think part of it is that once we got to college, we sort of choose our majors. That sort of led to a sort of branching point among a lot of our peers in terms of what accomplishments are expected of us, there's less of that sort of certain things you have to do being enforced upon you. So I actually felt, for me, Cornell was actually an easier time than high school. Now, that is not to say that
Cornell was easy.
Yeah.
Sure. But I think the hardest part of college for me was the freedom to do anything. I think it's the first time where you're, for me, away from home, that you have the opportunity to really leverage all that a huge university has to offer. And you can do a lot with it, or you can just sort of coast by. And either extremes exist. And I knew when I entered Cornell that I had certain goals I wanted to achieve, and I had an inkling for how I wanted to achieve those things. So I was able to get engaged in research right away. I was able to participate in different engineering project teams that suited my own interests. And I sort of committed to those throughout my entire duration there, just because, again, I felt they were helping me prepare me for the career aspirations I wanted to achieve.
That's awesome.
Now, did you come to Case right after?
I did.
Okay. So then you must have applied your junior year.
I did.
Okay.
Yes.
Yeah.
It's tough.
So that's you knew from the beginning, MD, PhD was the thing for you. Did you apply to Case for undergrad, by the way?
I did not.
Okay.
But I knew that Case Western had a very renowned medical school, and their MD PhD program is actually the first one that was established in the country.
Oh, really? I did not know that.
I believe it was 1956, before the NIH had any sort of program that sort of allowed schools to fund MD PhD students. Case had a program sort of designed not too different from the current one to help people who had interest in doing both medical science and investigative research.
That's awesome. I did not know that.
Yeah,
that's really cool.
I mean, we knew Case was 50 years old. Or the United States was 50 years old when Case was found, right?
Something like that.
Or it was it's like Western Reserve and Case University,
Case Institute of Technology.
Case Institute of Technology. So you said that you were able to get into a research lab right when you got to Cornell.
Yeah.
Did that influence any of your work that you're doing now as a PhD?
Not really. When I was an undergrad, most of my research was yeast biology. So I worked with yeast cells, whereas right now most of my work is therapeutics and in a mammalian context. But I don't think that's to say that was a worthless experience. Quite the contrary. I think when I started my lab early, I had a very enthusiastic advisor, and he would always engage me in this experimental process with mentoring me and giving me a lot of freedom to sort of push the project in any directions I so choose. I think that freedom, in a way, allowed me to learn a lot. it probably wasn't the most productive for me, but I had that opportunity to investigate a lot of different directions. I felt, even though productivity-wise it wasn't the best, but I felt like me being able to explore so many different facets of the biology I was investigating would end up helping me in that I would like to turn to many different approaches, even in my current research, to sort of understand my system, to find the most creative and balanced way to approach a challenging question, and hopefully design new therapeutics, which is my current research, that can have eventual benefit.
Were you in that lab all 4 years?
I was.
Okay.
Mm-hmm.
That's pretty cool.
And then did you do collaborations with other places in that specific lab?
Not so much. I think we were pretty self-contained, but eventually towards my senior year, my project got to a point where it made sense with new emerging technologies from a lot of different scientists that my advisor encouraged me to reach out to these scientists directly and just talk to them to get a sense of how they designed these technologies, how I could use them in my own research. And although it wasn't a successful endeavor in my undergrad years, I still use some of those technologies and implement them right now in my own research with success. So I think having that exposure again to many different fields, having that freedom to explore and talk to experts in the field, eventually did help me understand how I can investigate my system a lot better than I otherwise could have.
So what I'm kind of hearing is, like, Cornell, you were kind of like in one lab, you guys were like self-sufficient until like your senior year, you were like reaching out. So Case Western, do you feel like that is the opposite? Because I feel like that almost every lab here is collaborating with everybody, just like whether it's to get experiments done, to get data, all that kind of, I mean, I work in a Marta Sai's lab, you work in Drew Adams' lab, and this is not the first time Yi Fan and I have met. We worked together, I helped Yi Fan with this project, and it was great. It was so cool to come in and like labs come in and we do harvest together, and you know, we're emailing and always talking to each other, and it's super cool. So do you like that kind of atmosphere and culture here at Case, and how has that affected you as a PhD?
So I think, you know, it's not to say that there weren't opportunities to do that in my undergrad lab. It's mostly because we are at East Biology Lab and we sort of had a lot of our own techniques down. But here, I almost feel like the stakes are a little higher in the sense that we're not working in East Biology context anymore. We're actually working in a human context with therapeutic implications down the line. I feel like everyone in the School of Medicine here sort of has that understanding that something we develop in the lab now could eventually become something that has a lot of therapeutic benefit. And so I do think that one of the biggest, most important experiences in my PhD is the opportunity for collaboration. That, you know, having started working on my own system early on in my PhD, I was pretty self-contained, but eventually it got to a point where we recognized that this has potential and we want to bring out that potential as much as possible. So we reached out to people like Amar. We reached out to another investigator, Alex Huang, who's a pediatric hematologist oncologist, as well as a structural biologist, Sudha Chakrapani, to help us approach this problem from a lot of different angles and really help bring out the full extent of what our therapeutics can do. And we do eventually hope to leverage all of their experiences along with my own research to really push it towards something that can, in the long term, benefit a lot of people.
Yeah.
I have a personal question for you.
Mm-hmm.
So you said you left Taiwan when you were 5?
It was 8.
Oh, 8.
Yeah.
Okay. So I'm of Indian origin, but I was born in Nairobi in Kenya.
Okay.
And I came to America when I was 8.
Okay.
And I always have the hope of one day going back to those, both Kenya and India, and helping kind of structure their entire medical system, because they're technically third world countries, even though India has a huge population, but third world countries, and I've seen the medical facilities in both countries, and I believe that like the responsibility of a first world country like the United States is to develop things here, but eventually, you know, help the other parts of the world as well. So do you have hopes, and are you familiar with the medical system in Taiwan?
Not too much, since I was pretty young when I left, but I do know that Taiwan itself is actually a very advanced country. And a lot of its system has inspiration from the United States. For me personally, I don't have too many personal connections in the country, and I don't foresee myself going back to the country and sort of making a living there. But I do see that, I do appreciate that there are many who do, who are inspired by their origins and want to be able to contribute to their community in that way. For me personally, I've always felt that my home has been the United States. Most of my formative years have been spent in the United States. And regardless, I think this is a cool part about science. Science doesn't care about your background and origins. Science just cares about the merits of what you do. And I do feel that even if I don't actively participate myself in the Taiwanese community, that the work I do will have a global influence, and that's what I aim to do.
That's awesome.
That's a very good perspective. You
That's
have
awesome.
you have a very positive outlook on like everything, you know?
You found what your parents do.
Yeah, so my mother she works in multiple jobs. She's not very skilled. Neither of them graduated from college. So my mother usually works several different factory jobs, where she jumps between different factory jobs depending on the need. My father, when he moved here, he did mostly IT-related work, and that's sort of how we've been spending our lives.
So you
here.
don't have any like medical
Yeah.
influence in
I
your
don't.
life, yet you're
Not at
still
all.
pursuing.
That's why they push me really hard to get on it. Yeah.
That's awesome though. You're answering to like, you know, like a bigger purpose. In your life.
Yeah. Do you have siblings? Do you have any brothers? Sisters?
I'm actually an identical twin.
You're an identical
Oh, wow.
twin.
Yeah.
No way.
What is your identical? What is the name of your identical twin, and where is he?
Yeah, so my identical twin is Yi Fan. So basically in our language, our character, there's one character difference in our names. He is actually autistic, which is kind of an interesting thing considering we're identical.
Identical, yeah. Wow.
Yeah.
So I'm not either that means I'm autistic too, or something else weird happened. Anyway, but because of that, he currently works in an Amazon warehouse where he just sort of, even though he's autistic, I find that he's very independent and he likes to just go for opportunities when it's presented to him. So he really enjoys his work. He puts in a lot of effort into his work. I think he's been given the Best Employee Award for 5 months straight in a
That's
row
awesome.
at Amazon warehouse.
That's great.
So I feel great for him, but he is a little bit more academically challenging some ways, and so he does the best with what he can, given what he has.
I've worked in an Amazon warehouse, and
Yeah.
I'll tell you, it's hard to stand out. There's a lot of workers there, and they're all really hard working,
Yeah.
so that's awesome.
That's great. That's
Yeah.
great.
And they're all in the city?
They're all in the
They're all
city.
still back in
Yeah.
New York.
Nice.
So, do you have aspirations of going back to New York, or do you plan on staying in the Cleveland area?
I'm still debating that. So I think for at least the next stage of my training, I think this is something that my advisor would suggest that I do too, is to really branch out. He really recommends that we, and I agree with this, to get training from different areas of the world, to experience different ways that people do science. And, you know, long term, if you want to settle in Cleveland or New York City, sure, but at least for training purposes, explore other options. So I would love to be able to go to the Boston area for the next stages of my training. That's where my advisor did his postdoctoral and graduate training, and the biotech community there is booming. And I would certainly love to participate in some of those opportunities. Long term, I haven't decided. I think it would be nice to be able to go back to New York City, if only just to support my family a little bit. But I think I'll let the opportunities decide where I go.
That's great.
In the near future, I think that, like, in my opinion, Boston and, like, California, they're kind of saturated when you think of biotech. Whereas when you look at Midwest, you look at places like Michigan, I don't even know, like, New York.
Penn.
Is there a lot of biotech stuff in New York?
New York, my understanding is not so much. I think New York is very much a financial and entertainment center, whereas biotech hubs are sort of, you know, your Boston, your Bay Areas, as well as emerging areas in the Midwest is sort of where I see the biotech industry takes bloom.
Yeah. I see Cleveland as like an area in the future that's like really like a hub. Because even geographically, you look, Michigan's right there, Chicago's right there, New York is right here, Philly's right here.
Don't forget about Cincinnati down
Cincinnati's
there.
right there. Yeah. Cleveland is kind of like in the middle of it all, and we have Case Western, we got Cleveland Clinic, UH, Metro Health. There's like really good
Yeah,
facilities.
so I do agree that the Midwest, because of its sort of up and coming nature for a lot of these industries, could be a very exciting time for long-term settlement. And I'd be very excited to be, if I can get a faculty job at Case Western,
Is that something that you're?
I'd be very open to that.
So
That
with
would
an
be
MD
great.
and a PhD, you would want to do more research and be faculty rather than like your own PI. Would you want to be a PI?
I think so. I think that's sort of the personality that I've associated myself with, that I really like investigative research. I like asking sophisticated questions around the underlying biological principles.
Mm-hmm.
And I like making new discoveries. I think a lot of important therapeutics that have been developed sort of all have their origins in a basic scientific discovery.
Mm-hmm.
And I do feel like there's a lot of opportunities there, in addition to the up and rising technologies across many scientific disciplines, that I want to be able to participate in that investigation process and using those information push forward new therapeutics that can be very exciting.
That's
now, I
great.
actually have a follow-up question
Yeah.
because you said discoveries have a very common biological basis to them, fundamentally, right?
Sure.
So, in your lab, for like when you guys make new compounds, like
Mhm.
through chemistry,
Yeah.
do you take an existing compound and derive something from there, or are you combining two compounds, or really making a novel compound?
I think that depends on your end goal.
Yeah.
For us, I think there's an opportunity for example, drug repurposing, where you have a known molecule that is established to do a particular function. You believe that this particular function can be applied to another disease area, in which case you may begin to modify the drug in such a way to improve the way it engages its target protein, to improve certain other parameters that would be better suited for that criteria. For us, it really began with sort of screening, where we found a molecule that doesn't look like anything that we've seen before, having a particular function. And once we sort of began to understand exactly how it's doing what it's doing, that we then had a more agnostic approach to how to modify its structure. So we synthesized then a lot of different structures that all look very different, but all share the same mechanism and functions. And then we sort of pick and choose which sort of structural series are more aligned with certain pharmacologic parameters that we like as a therapeutic lab. And then we move forward from there. So again, sort of depends on what your end goals are and what your starting points are. And then, a lot of it is sort of guess and check work, but you can make really good guesses and checks along the way, depending on what your starting and end points are.
So this is a good segue into let's take like 10 more minutes to talk
Sure.
about your PhD work. So this is a project that I got to help kind of at the tail end of, but this is something that's been happening for the last 4 years.
2 years.
Two.
Mhm.
So I mean, this has taken up a very good chunk of your time
It has.
as a PhD
Yes,
student.
very
So
much.
me being on the project, I want to learn, what made you and, Drew go with, looking at this certain type of drug and this certain type of disease, and, what was kind of like, how did those dominoes kind of all fall?
So the project started when the ideation stage started when Drew was still a postdoc at the Broad Institute, where his inclination and approach towards science has always been he's interested in therapeutics that have a lot of translational potential. And so one molecule was sort of identified as an inhibitor of T-cell activation. T-cell activation being an important part of a lot of immunological disease. And what was interesting about the drug was it seems to have very selective activity against T cells, which is something that's pretty rare in small molecule biology. And also that it didn't, compare to a lot of standard clinical therapies, it seemed like this one was much better tolerated than anything that's available out there, including the ones that are used in the clinic right now. And so, but the problem was this drug, even though it had so many promising parameters, people just didn't know how it worked. And probably because of that, it was never able to progress towards anything beyond an interesting observation. But I think what we had when we first started was the wisdom that had been accumulated for 2 decades since the observation was made. And so, again, we are a chemical biology lab, which means we combine biology and chemistry. Chemistry is a central aspect to what we do. So we were able to modify the drug in interesting ways, leveraging the chemistry wisdom that has accumulated over 2 decades to really get a sense of how this drug is working, the target that it's acting through, and how through that target it's exerting this T cell activation effect in a very selective way. And so what that led us to conclude was that it actually targeted a protein that is very common in all cells, but this protein can behave in different cells in different ways. And we have also designed a way to target this protein in a very safe way so that we can improve its safety profile in both animals and hopefully eventually humans. And given that it's in a space such as T cell activation and immunological disease, there's a lot of disease burden around the world around this particular space. We want to be able to leverage these new findings that we got from chemistry to be able to design something that has a lot of benefit but minimizes a lot of the shortcomings of traditional therapies.
And when I think of inhibiting T cells,
Yeah.
that's like a big risk, because what if you get an infection and you need those T cells? So what are some disease indications for, like, I guess I can think of, COVID caused a ton of inflammation in you, like all kinds of cytokines, which has a big T cell activation. So I feel like in diseases like COVID, T cell inactivation would be beneficial.
And I think that's part of why this project is exciting, because the original observation was that the activity was very selective towards T cells and not so much the other cell types. So in a sense, you're really shutting off the T cells, but you're sparing a lot of the other side effects that are associated with traditional therapies. So that's one aspect. In terms of clinical indication, that's something we're still actively trying to work out. And that partly stems from just our lack of understanding about what's the exact level of T cell physiology that modulation of this particular target, as well as our drugs, are having on different populations of T cells. Now, having said that, Nick and I have been collaborating together on several different disease models, including idiopathic pulmonary fibrosis, which currently has no known treatment to the best of my knowledge, and graft versus host disease, where, again, the traditional therapies, although they work, come with a lot of devastating side effects. And we believe that something like ours, which we have demonstrated working both, could be a way to either open up the field around pulmonary fibrosis or to improve on existing treatments around graft versus host disease. And given that both of these diseases have very different underlying causes, different etiologies, that we think there's opportunity for it to expand into many other indications. We can be more intelligent about it, which is a goal that we want to achieve in terms of understanding the underlying T cell physiology and using that as a way to guide what sorts of diseases are most likely to succeed. But again, based on what we have so far, we think it has pretty wide potential.
That's awesome.
It's so cool.
Yeah, I bet.
It's so cool.
And I have one more technical question.
Yeah.
So in the world of chemistry, when you see a molecule, is that mainly just HNMR? So you're seeing the emissions, or do you have other sort of ways to look at it?
I think at a basic sort of organic chemistry class level, you usually use things like the infrared radiation, IR, you use NMR, sometimes mass spectrometry. So we use a combination of all these different methods to sort of look at a molecular structure. And the technology, although I'm not personally great at it, the technology is such that the underlying physical principles is that whatever graphs you generate from those techniques, you are able to extrapolate the exact structure of the drug that you synthesized or you discovered.
In organic chemistry in undergrad, I remember almost every week we were running IR. We only got to run NMR once, and I went to a tiny little Catholic university, right? And our NMR was like the size of a computer. And there are schools, and even in Ohio, that have it that are the size of buildings. These magnets are ginormous to pull these little hydrogen molecules to read these things. And that's one thing, it's cool to see a line structure, like an organic chemistry line structure, but there's so much work that goes into
I think that's a really cool part about science, where
that's so cool.
People can extrapolate this information just from random lines and graphs, and everything is so consistent that, if you imagine if there was any underlying flaw in the theory, that everything would fall apart. Like, there's absolutely none of that.
It's wild.
So you
That's
can
wild.
make hard conclusions
Oh,
from
yeah.
from data. Like that's amazing.
Yeah.
I actually got to sit in on Yi Fan's talk that he gave about, I'm going to spoil it. Yi Fan's publishing, or in the works of publishing a paper in Nature for this work that he's doing. So congratulations for that. That's absolutely incredible.
Thank you.
So I had the opportunity to go and listen to his talk. He gave it was in the
In
BRB.
Boston? Oh,
No, it was in the BRB.
It was a seminar.
It was just a seminar. It was
Yeah.
a seminar just over his project, and it was incredible just to see. It was basically like from start to beginning, like all the background, and then going into like how they found it, and it was all the chemistry, and then it went into all the collaborations of what they were doing with the molecule, and like working with Dr. Desai's lab and doing graft-versus disease and fibrosis is just like, a small percentage of what they're doing with this molecule. It's absolutely incredible, and the way you don't think that your questions are hard. The questions that the people asked him during that lecture or seminar, I would have crumbled. I would have been like,
Were
oh
they
my God.
extremely specific?
Who was the gentleman who was sitting in the middle row that asked you like the 5 questions in a row?
He had expertise in sort of epigenetics, which is a mechanism that we are trying to elucidate around drug. So he was very particular about the mechanism I was proposing, and rightfully, I think.
Absolutely. I was just saying, you answered them with so much grace. I couldn't believe it. And it really showed. At the end, he was like, "All right, thank you." And at the end, it showed
He's the expert.
you got it, man. You basically defended your thesis at this
2 years
point.
in, 2 years
Seriously,
early.
yeah, early.
I think that's a cool thing about being a graduate student. You start off inexperienced, you need a lot of guidance, but over time, as you sort of devote that time towards your project, towards that purpose of building this, what you have, something that's unique to you, towards something with a lot of benefit to a lot of people, that process of being engaged really trains you to be an expert.
Yeah.
And during that seminar, as Nick was able to describe, I just felt like there was nothing that I didn't know that other people, there was nothing there that I didn't know better than other people.
Yeah.
And I felt like I was able to carry myself, because I engaged with it so much, with the confidence of someone who's worked on it forever.
And I think that has to come with being an MD PhD. You cannot be a doctor nor a PhD and get asked a question and be like, well, it could be this. No, it's going to be like, no, it's this.
It is,
And I've studied it and studied it and
Yeah.
studied it, and it is this. And that's incredible. That takes a lot of time and effort. And I was so impressed. I was so impressed.
No,
It was
I
so
can
great.
imagine.
It was so great.
So now, as a person in
Yeah.
the field of medicine,
Mm-hmm.
what are some new cool technologies you've seen? CRISPR is obviously revolutionary
Sure.
for our industry. So what are some things, how do you think maybe AI will impact drug screening? What new technologies in the field of regenerative
Yeah.
medicine or stem cells in general?
What
do you
excites
think-
what excites you?
What excites you?
Yeah.
Other than your own thing. Can't say that one.
Of course. I'm generally actually someone who's a little bit more hesitant about technologies. Oftentimes, I almost feel like they are people jumping on the hype train a little bit.
True.
But having said that, I do think there are a lot of opportunities for things like AI, and even staying within the sort of drug development field, there are very exciting developments that I think could have a lot of potential. To address the AI, I think I'm not personally too sure about the prospects of AI aiding in drug discovery anytime soon. I think it can help facilitate some of the processes.
Yeah.
But I think ultimately, my understanding is that AI works in the boundaries of what has already been known and sort of facilitates that processing away much faster than an average person can. And so I think it would work really well in terms of working within those boundaries, but in terms of discovering the unknown, I don't know whether or not it can take us there yet.
Yeah.
Perhaps in the future, but not quite right now, to the best of my understanding. In terms of drug development, I think a lot of that comes down to exciting developments in chemistry, that people are able to sort of leverage chemical techniques, apply them to biological systems, manipulate them, and in doing so, understand biology that has never been studied before, and expose new therapeutic opportunities. So I will mention one person, Carolyn Bertozzi from Stanford, who recently won the Nobel Prize in Chemistry. she was one of the pioneers in developing a technique called click chemistry. And recently, I believe around 2-3 years ago, she published a big paper in Nature documenting a new type of therapeutic that has never been documented before. I believe before the paper was even published, investors were willing to pitch in millions
Wow.
for this startup company founded at Stanford, and I think it's doing very well right now. So I think, again, there's a lot of knowledge out there, but you'll always be surprised at how people are able to take existing knowledge and completely transform them into something new and unexpected. And I think she was able to do exactly that with the technology she has, and I think that's very exciting, and I can only imagine what other people can do with their own ideas and just expand in ways that we would never predict.
Yeah.
Did you watch the Nobel laureate video?
I actually did not.
I watched it, and
You did?
she actually talked about click chemistry.
Yeah.
And I was like, that's fascinating, because I didn't know it was like a Nobel Prize winning discovery,
Yeah.
because we learned about it in like nanomedicine, right? We learned
Mhm.
about how things click based on charges and everything. And it's like,
Yeah.
it makes
Also,
sense.
too, with like there's like a ring with 3 nitrogens
Yeah.
and like
Yeah.
it's funny. My organic chemistry teacher in undergrad, more organic chemistry for undergrad, right? He taught us click chemistry. Like our last lab of the first or second semester was click chemistry.
Yeah.
And it was really fun. It was really cool to see like the mechanism. And I didn't realize that was
Yeah.
going
It's
to be
actually
Nobel Prize
Yeah.
winning.
It's a
work.
very recent development. I think it was only around the turn of the century that it was first sort of coined and then eventually developed slightly. And so that's really the click chemistry is something we use in the lab actively. It made a lot of things in sort of studying drug target interactions almost trivial in some ways, whereas it used to be a very challenging problem. And sort of the idea behind click chemistry is that it is bioorthogonal, that it is dependent on functional groups that do not interact with biological systems. That allows you to have a lot of control over this molecule you synthesize and how you can and you can use those functional groups to manipulate biological systems at very specific times and at very specific places. And so that has really transformed how chemistry can be applied to biological fields, right? If you think about traditional chemistry, you are heating things up in like a glassware at super high temperatures, with a ton of acids, bases. You would never be able to do that in a biological system. You'll completely destroy it, right? But the idea of click chemistry is that it is biocompatible, that you can do this in living systems with pretty much minimal repercussions to that particular system. And so you can begin to see things, manipulate things with a level of precision that cannot be achieved before, and in a way that cannot be achieved with traditional biological techniques either. So I think the Nobel Prize is certainly
Well
deserved.
deserved.
Very much.
All right, well, I have one more thing
Yeah.
before we end this. I think we're at like 45 minutes.
All right.
So,
Yeah.
spinning back to the AI really fast, I had a lecturer come in, or I had a teacher come in, a PhD that works at Case, and you're saying how you don't necessarily see how AI can build because it's only based on what we humans know. And one thing that he's studying is a combination of AI and physicians looking at rectal cancer and looking at MRIs and being able to spot out different spots that, maybe the computer saw that the doctor didn't see, and vice versa. So they found that when the computer did it, it was like 75 to 80% accurate, and the doctor was the same. But when you combine the two, 100%, and they were able to guess out when you would need surgery by like the week. Like they would be able to, like, it's 4 weeks, 8 weeks.
Yeah.
It's a diagnostic tool, basically.
And I thought that was such a cool way. AI is not necessarily here to
Take
just
over.
tell us the future and take over.
Yeah,
It's here to
no.
assist us.
It's assistant.
Absolutely.
It's assistance. So
And I think that's, at least right now, that's where it really shines. I think there's a lot of talk in the healthcare industry to implement AI in a lot of different ways. So, for example, one of my friends is trying to work on a project to aid in sort of diabetes management. Now, diabetes is very complex with a lot of genetic variables, a lot of lifestyle variables that all contribute to the disease.
Yeah.
And as a human, it's hard to sort of take any individual person, integrate all of their lifestyle and genetic factors, and sort of then come up with the best plan that makes sense for this patient. But I think this is where something like AI has a lot of benefit, because an AI is able to sort through all of that information extract patterns from a large cohort of people, and then based on how these people behave, how they respond to different therapies, that the AI can use those patterns to make a best prediction that a human can't.
And
Right.
you know what would go hand in hand with this? Let's say if somebody kind of like democratizing genetic testing.
Mhm.
So like you can get your genes read today, and in 2 years you can get them read again and see the changes in expression, right? And that can also hint towards which disease states you're going towards. So I feel like there's multiple tools that can be used in the future
Mhm.
with also consistent testing
Yeah.
to find out changes in expression.
Mhm. Yeah, I think medicine is always lags a little behind scientific innovation, and
Yeah.
probably rightfully so.
Yes.
Mhm.
But right now, with all the talk about things like genomic sequencing, how that can help inform of disease, I think we're really just in the infancy. Right? As someone who sort of works in the investigative sciences, how sequencing technology have been applied is incredible.
Yeah.
I think if we can then eventually translate some of these applications towards routine medical use, I think there could be a lot of benefit. I think there will be a lot of hurdles to get there, but I think once we get there eventually, I think the way we interpret results from genetic tests, genomic tests, will become so precise and refined that we can really make medicine as personalized as possible.
That's incredible.
Amazing.
All right, well, what an episode.
Yeah, that was
What an
awesome.
episode.
Thank you for coming.
Yeah,
Thank you for having me.
Thank you so much
Yeah.
for coming on. This was great. Like I say, if you ever want to come back on, share stuff, we'd
Mhm.
love to keep us updated on the paper.
Yeah.
We'll put it on our LinkedIn. We'll tell people about it so people
Okay.
can read it and everything, because that's so cool to be
Yeah.
published in Nature. So thank you very much for coming on. Once again, you found.
Mhm.
And again, to you guys, thank you for listening. Thanks for tuning in. Remember, like, subscribe, comment, questions, email us. But this has been another episode of Cells to Cell. I'm Nick. That's Heen. We'll see you guys.